Good evening, everyone. Hope all of you are having a great day. Thank you for tuning in to this session on a Sunday evening. I'm Chinmay Shah from Mumbai, and I lead the PyDP team over here at OpenMined. I have a computer science background, and I graduated this summer. And today I'll be talking about differential privacy using PyDP. So the format of the talk is like in the first few minutes, I'm going to talk briefly about differential privacy, and then I'll go into a bit about PyDP RT. Following which we'll dive into the code. I think you already must have received the GitHub repo. I'll just put it in the chat once more. You can open these notebooks using Google Colab and you can run it parallelly at the same time. During the coding session, as Yafa mentioned, you could ask any questions in the Q&A and I would answer them. And following the coding session, I'll be talking about where PyDP is headed next and followed by team Q&A. Yafa, can you share the GitHub link with everyone?
Okay, just I will just share it now. So,
Yeah.
okay, I think it's okay.
Yeah. Okay. Yeah. So I'll start with what is differential privacy. So in the sessions that have been happening yesterday, many speakers who are more qualified than me have already explained what differential privacy is. So I'm going to try to explain that in a very simple manner. Imagine you have two datasets A and B, and the only difference is they differ only in one record. That is, assume that your record is present in dataset A, but it's not present in dataset B. So the idea of differential privacy is if even if only two record, even if only these two, one record is different, then also you should get the same output with or without your data. So with this founding principle of differential privacy, uh, we try to achieve. We have built differential privacy PyDP library as well as all the other work. So this work was started by Cynthia in 2006, and it has progressed since. And recently, like for past 2 or 3 years, this industry has really boomed, or this sector. So what differential privacy usually allows you to, it allows you to do aggregation functions over a data set. So why we need to talk about differential privacy? The, in 2007, Netflix organized a Netflix recommendation engine competition where the participants were asked that okay, here's the record of all the Netflix users, of course in anonymous format. So we want you to help us build a better recommendation engine. So this was a $1 million competition. So what it was asked was like they've released a data set which has a anonymized user, so some user ID, along with the name of the movie they have watched and the date at which they have watched, along with some other metadata. And what the participants had to do was try to predict which movie are they going to watch next. So or which movie the user will watch next. So what was done was like a wind who took a different data set. He took a IM public data set of IMDb that was available, and what he found was like most of the users who recommended who rated something on Netflix also rated something on IMDb at the same time. So they just correlated just two different data sets. So for example, if I watched something today on Netflix, I rated it. So back right now it's just thumbs up, but back in the days there was a rating system. So I rated something on Netflix, and then at the same time I also went on IMDb and also did the same rating. So I mean, the Arvind, like he was able to identify with around 97% confidence that you know what, this was Chinmay who has watched all these movies. So with this, like all the unique identity of all the Netflix users they were able to identify from the public released anonymized data sets. So the anonymization is not enough. Like anonymization is the technique that we are using these days when we say, hey, you know what, I want to release this data set publicly. So you remove all the personally identifiable information, but as this Netflix price fiasco tells us, this is not enough. There are various examples, right? For example, there was this Boston Medical data set, in 1980s, where the government released all the medical records of people in Boston, and even that didn't work out. So these are the two different famous examples why we need differential privacy and anonymization is not enough. So what DP means in the current context? Imagine you have a huge data set. As a company, you have a data set of all the users with a unique UID. And in the current context, GDPR context, imagine a person opts out from a data collection. So they can ask whether they might exercise their right to be forgotten rights exercise, or they might just say that, you know what, I don't want to be part of the data collection anymore. So what happens is, like, previously they were already part of your model, so that each of the response or the data point or record affects the model that you have computed, right? So what happens next is, like, what if I remove the data point? That would imply that your model has changed. The result of your model would be different. So in this case, this is the reason why we need to think about differential privacy. So using differential privacy, what it means is, like, your data would, using differential privacy, it would mean that your even if you remove this one person, you should expect the same result. So with this, differential privacy is more important than ever in this current context, and in the world where we are heading it, where we have privacy inbuilt by default, we should be having more differential private protects inbuilt in all our pipelines. So a bit about PyDP. So PyDP is a differential privacy library, the Python differential privacy package that we are building here at OpenMined. So we have already released this on Python on PyPI, so you could download it at pip install Python DP. It has already got 13,000 downloads on PyPI, and we are on a stable version that we had released last month. You can also find a PyDP on Docker Hub, so you could just use the Docker engine. We have 35 plus contributors already, and right now what we do is, like, Cooper has released the differential privacy library. Miguel talked about this earlier in a stock. So what we do is that library is written in C++. So we have wrapped that library in Python to make it more accessible. So data scientists and ML engineers across the globe could start using differential privacy in their current work. Documentation can be found at pydp.read.docs.org. So we have like 36 contributors already from across the globe, like from US, Europe, Africa. Uh, we have a bunch of folks from India, and then even moving to East, we have people from Indonesia as well as Australia. So pretty much we are covering up like almost the all 7 continents. So without further ado, let's dive into tutorials. Feel free to ask any questions in the chat or in the Q&A session, in the Q&A chat pod by you have any questions. So what you could do is you could run the tutorial, run this collab notebook at the same time with me if you want, or you could just watch this thing. The in the GitHub package, in the GitHub link, you should be able to download this notebook as well as run this thing at the same time. So let's talk about PyDP, and let's start with a very basic thing. So in this notebook, what I'm going to do is I'm going to demonstrate how to do you differentiate privacy using PyDP, or like a proof of concept for differentiate privacy. So so what we do is, like, we're going to protect some user from something called as membership inference attack, or MIA. So idea behind differentiate privacy, as I talked earlier, is we should not be able to identify a unique user or unique individual user. So to prove that, what I'm going to do is I'm going to I have a data set, and I took a subset of the data set by removing exactly one record. So the record, two data sets differ exactly in one record. So we are going to use differential privacy to prove that using Python PyDP, that, you know what, if you apply DP, like, the unique identifier or the user that we have removed will not be identified. So the in the first slide, when I explained what is differential privacy, you could have seen that there was one user that we had removed, and we were still achieving the same results or the similar results. So we are gonna try to achieve that over here. So how we are doing that? We have generated a synthetic data set of 5,000 records. So we're completely generated using a script, which has a unique identifier such as name, email, and something a unique constraint called sales amount, where like each user uh, has some sales amount, like the credit card amount they have spent at some restaurant or anything. So what we're going to do is we're going to demonstrate differential privacy using this thing. So okay. So let's start the installing PyDP using Python-DP, and we are importing bunch of libraries. So we are importing pandas because that's how we are loading this CSV files, statistics for just showing for calculating the raw sum, and then NumPy and matplotlib for doing the plots. So over here you could see that we have imported a data set. So we have ID, first name, last name, as well as email. So these three columns make a unique record, and then we have a sales amount that for which we are going to apply differential privacy, and state is a number. So this is a US data set. Now what we are doing is we are creating uh, so we have records of 5,000. So we have divided the notebooks into 1,000 records each. So we are just loading all of them together. And what we're going to do over here is we're going to combine this 5,000 records into one single data frame. So I'm just concatenating that using pandas. And if you could see the size of this new data frame, it's 5,000 records with uh, six columns. So ID, first name, last name, email, sales amount, and state. So to prove differential privacy, what I'm going to do is I'm going to remove exactly the first record uh, from our system or from our record. So here is our original data set we have, which is Osborne, and in a redacted data set, which we generate synthetically. What we are saying is, you know what, start from the first record, don't or the second record. Don't include the first record. So as you can see over here, it starts from the second record. So we're going to do something very basic at the start. We're going to take sum, normal sum. So the normal sum, the mathematical sum that we use daily. And we are just making sure that, you know what, the difference between the original sum and the record, and the and the new sum which has only one record missing, that amount actually equals to the amount of the first record, or Osborne's record, or Osborne's sales amount. So as you can see over here, when if I had another data set for which I had a spending of each user, let's say credit card details of each user, where I had an amount of that amount as well as the time it is spent. But over here, even the exact amount, in this case 3194, if I have this exact amount and I have a rough timeline, I would be able to identify that, if someone releases this data set by removing the first name, last name, it's just sales amount and state. I should be able to identify that, you know what, this is Osborne's record, and Osborne was the one who actually went to buy. So that's the reason why we say we require differential privacy. So what we are going to do is we are going to apply PyDP. So over here we do something called as bounded sum. So a bounded sum is a differentially private algorithm, which is a part of a bounded family of functions. Over here, this is like the differentially private method or way of doing the sum. As you can see in the document, it computes the sum in a differentially private manner. Over here, the first thing you need to do is provide epsilon. So I'm going to just start typing over here. The first thing we need to give is epsilon. So that's basically how much privacy you want to give it. So we could say any number, but usually we say log 3 or 1 or 1.5. So that's for calculating how much noise do we want to give, like privacy versus noise, sensitivity, this thing. So it's basically a floating point number. and let's say we are going to use epsilon of 1. The second thing we need to give is the lower bound. So lower bound is the uh, minimum amount that needs to be set. So over here, what happens in this bounded algorithms is when you mention a lower bound of, let's say, 5 or 10, all the amount that is less than 5 or less than 10, for example, if I had a spending of 7 or 8 rupees, that automatically gets upgraded to like set to lower bound, that is like the 10 if I set it over here, or 5 in this case. So all this lower value are clamped to 5. And the next thing is setting the upper bound, so that's we're setting 250, so that's the maximum amount someone can spend over here. So we are clamping that if anyone has a spending that is more than 250, so let's say it's 255, 300, or 350, it automatically gets set down to a pound. That is in this case 250. And the last argument is float. So what happens is the PyDP actually it works underneath with C, it's written with C++ under the hood. So we need to identify, what which data type it has to use, whether it's float or int, because if you know that your data type is going to be int, you don't want to waste all the memory that's available there. So float is 8 bytes and integer is 4 bytes. So you don't want to wait 4 bytes for each record. So it's just a trade-off. Like by default, if you don't set anything, PyDP takes it as float, but we would recommend that you need to if you're sure that your data type is integer, then you might use it to save some memory. So I'm just running it over here. And what you're going to do is and then uh, once we have calculated created the object of bounded sum, we can call something called as quick result. So PyDP provides two methods for calculating something. One is like you can add entries and then calculate results, and another is something called as quick results. So in the quick result, we are using up all the epsilon which we had selected earlier or mentioned earlier. So the quick results uses the all epsilon, and argument that quick result takes is the list it needs to list where it needs to work on. So over here, what we're gonna do is we are gonna calculate gonna give it the sales amount from the original data set, which also had the OSPAN. So I'm just gonna run that and rounding up to 2 digits, and let's say we got a number. Uh, Now what you're gonna do is we're gonna do the same thing, but with a redacted data set. So over here, I'm gonna do the add entries method. So first of all, we're again creating a bounded sum object with epsilon, lower bound, upper bound, and a data type. And then creating on a directory. I'm calling it add entries. So add entries, you can add entries as you want. So you could, for example, let's say if you have a huge array of number, then you cannot simply pass it to a list like that, because you'll need a generator that actually iterates through this list. Because if you put in the whole list into the memory, your memory overflows and bad things happen, and your program might crash actually, because Python is good. So what you're going to do is you could, if you have a generator, so you could use add entries method. So over here, I'm just putting the whole sales amount at the same time. But what we could do is, like, if we had file list, I could put in file list at each time and go through this thing and add them over here. So it would be like, and we are calculating over here, calculating the sum. So let's just try doing uh, adding each data, like using add interest function as it is. So we have we have df1, df2, and all of these 5 data frames. So let's try actually doing that in this case. So you could also try this along with me. Mhm. So we are gonna say, what, df1. First of all, what I'm going to do is actually going to do reset function. So what reset does is it removes all the data, as well as if there is any epsilon used, which we'll discuss in the next example. So it also removes that. So I'm gonna add five of this list. So first of all, let's execute this command as well as this command. So we know that the result is something like, okay, over here you could see the result. So I'm gonna add these pi data frames, and then I'm gonna call what tag and dot protect, and I'm gonna round it up to 2 decimal points because it's a floating point number, so mm, it's with floating point precision. So let's just run it, and as you can see that uh, then you could actually use a generator and give it the data, and it generates the same thing, and it gives you the almost similar result. So add entries works if you have a huge data set. So what we're gonna do is we're gonna do something like we're just gonna do some assert some values and see if these things are working. So some of sales were using original data sets, and we are gonna do some of original data set in using differential privacy. So as you can see, the results actually differ a bit, and we are just gonna do that using a retracted data set. So, and we're also asserting that what the DP sum is not same as the actual sum. So you could see that the difference is also in the retracted data set. So now what we're gonna do is see the actual sum and actual value. So actual value is like 3194, but using differential privacy, you could see that the difference in these two data sets is like 239. So what happens is like if you had a different data set, let's say a completely new data set, which I mentioned earlier, the credit card data set, you could be able to identify by saying that, I'll see all the 3194, and I know this restaurant name, so you could just identify the name of the user, Osborne. But using differential privacy, the Osborne's identity is protected, and if they release this data set by any chance, uh, and if you apply differentially private operations, you should be saving the privacy. So let's just try to put this on a chart. So as you could see, differential DP value in the original sum and in the redact sum both differ a bit. So and this original sum and the redacted sum just differs by 3194. So you could see that the values actually differ. And as and like the takeaway from this notebook is like we can protect users or the data from a MIA attack using differential privacy, as we had removed one record and seen that could not actually find out which that record is using DP. So now I'm going to jump to the second notebook, in which we're going to talk about some DP in a pseudo real world example. So you could just open that up. So this is something called as a reference demo. So this was released by Google in the original example itself. So they have released this in Java. This example is in Java, but we have at PyDP we have ported this code to Python, and we are demonstrating this over here. So in this tutorial on this notebook, what we're going to do is we're going to use all the functionalities of PyDP in a pseudo real world example. So consider a use case of Alice, who is a restaurant owner, who has been asked to prepare some statistics by investors, and also has an advertisement partner. So what advertisement partner might do is like they might do some hyper targeting of ads, like what's been done today, and she wants to avoid the same. So what she has been asked to do is she wants to count on how many people come on each day of the week, and the second is how much revenue does each day of the week generate. So for example, whether I'm getting more business on Monday or Friday, and the count is basically like how many people are more people coming and buying some less amount, or like this is something as a data scientist that you might be doing. Like for example, even if 800 people are coming and spending just 400 bucks, or like if 1,000 people, or if 200 people are coming and spending 400 bucks, so you want to see that is the revenue and the count in direct proportion, or how it's so that might just be a reason to count, or it might be just because you're curious that on what day like, what revenue occurs. So let's start with the thing execution. So we are gonna install Python DP as default. In this notebook, we are gonna use two methods: bounded sum and count. So for revenue on each day, we are gonna do sum, and for counting, we are gonna do count. So again, some default library match statistic expanders, NumPy, matplot for doing some plotting. So over here, the basic assumptions are that we are gonna open the restaurant at 9 a.m. Gonna close it at 8 p.m. because it's Euro, and we are just figured out that you know what, these are the valid hours for some calculations. And over here we are doing something interesting. So we are saying that the maximum amount that someone could the maximum a person can visit is like four times in a week. So a person can just visit in one, four times at max in a week. And then for the lower bound and upper bound, which I discussed earlier, we are saying that the minimum you will spend is 0, and a maximum is like 50 or 65. And we are gonna set epsilon as log 3. So first thing I'm gonna do is I'm gonna load this data set. So in this data set, we have this the ID, time enter, time span, and the money span, as well as the day. So each of the days, so day from Monday to Sunday, are labeled as 1 to 7. Money spent is in euros. It's an integer, and time spent. We could do some data analysis on time also, but we're not doing right now. We could do data. We could do something like find a mean of all mean mean of like how much time people are spending on each day. So you could try this as exercise. And visitor ID. So that's a unique count. So in this notebook, I want to introduce something called as concept of L naught and L infinity sensitivity. So L naught sensitivity is about number of times a unique user can contribute to different partitions. Okay, so over here partitions is, imagine something like for example, uh, you are for example, let's say you access Facebook through your mobile, your laptop, your other laptop, as well as your work laptop. So over here, your unique ID of your browser unique ID would be 4 different browser unique IDs. So you will be part of 4 different partitions, but essentially you are just one user. So the NO sensitivity is setting about how much times a person can contribute to different partitions. And the second is L infinity sensitivity, and that's about how much time a person can appear in the same partition. So in this case, in our context, it would be how much time a person can come up in the same day. Like for example, does he come again and again, something like that. So why we are needing this utility function is over here. We had set the upper limit that a person can come maximum 3 times a day or 3 times a week. So we are just capping this. So in this case, we are capping a person can appear 3 times a day. So we are just capping that number in this case. So let's start execution. So the first thing we are doing is getting the non-private counts per day. So here we are loading the data set and comparing it to each day and creating a dictionary of that. So it's just a normal dictionary banner. And the second case, what we are doing is first of all we are capping this thing. So we're capping how many times a person can appear in a max way. So how many maximum times a person can appear in different partitions. So he can only come like 4 times a week. So that's the cap that we are keeping in. And then we are just setting epsilon is log 3 that we had set earlier. Lower bound, upper bound, we need to set that over here. So what happens is if you don't set the upper bound and lower bound, PyDP actually allows you to set that, but it's a bad idea. But in count, actually, this lower bound and upper bound is not needed because we are just doing a plain count, so that's not needed. So we are mentioning the data type is int, and again we are doing this count, and we are just getting the result. So let's just see what happens. We are sorting this array, and let's see what happens. Okay, it expected 2 values and it got 3. So okay, I was just experimenting with this notebook a bit earlier, so that's the reason. So here you could see that without the results. So one is without differential privacy. So on Monday, 300 people came. Tuesday, same 300, and Wednesday, Thursday, 400 came, and in a similar manner. And using the differential privacy, you could see that the number is actually quite different. Like in the first case, differs by 16. The second case, it turns out it's same, but you could see that numbers actually differ by plus 5 to 6 numbers or something like that. So let's just try to visualize this a bit. As you can see that the numbers actually differ even by a small amount, but it's differing. So you're not getting exactly how much number, but you're getting a rough idea of how many people are coming in. So that's using count. Now, second thing we're going to do is we're going to calculate the revenue. So first of all, we are going to calculate the revenue in a normal manner using normal mathematical sum that we use. Second, we are using is something called using private sum using differential privacy. So what we are going is we are setting epsilon, setting the minimum and maximum amount that can be spent, setting L naught sensitivity. So that's amount like how many times a person can come in the restaurants. We are assuming that that's 4, and then for each day we are calculating the statistics. So we are using add entries and just casting that in result to integer, and we're returning it. And again, let's just see what's the answer. So what we could do is actually we could change this a bit, and we will not provide upper and lower bound in this case. So we are not providing these two values. So we're just providing at epsilon. So what happens in this case is the whole epsilon is used for calculating this upper bound, lower bound. After that, and then we are going to calculate this actual sum. So let's just not use the function. And since we are trying it out, we just print it out. So while that number processes, let's see that the sum that we had calculated earlier, the revenue, we could see that the number is differing. It's not exactly the same amount that's being spent. For example, for Monday and Tuesday, you could say the number is differing by a bit, and in the ending, when like we have huge numbers, the numbers, the noise that is added is also huge because, for example, if you have 100 records, you want a bit more noise than compared to when you have 10 records. So as you could see in the graph, mm, the numbers are differing. They are not exactly the same, but they're similar. So that should actually serve the purpose when you want to know the trends. Okay, epsilon is not defined. Cool. As you can see over here, I'll just sort this thing out, or we could just compare it over here with this number. So with differential privacy, this was using the earliest. So this is the function that I just read now doesn't take lower and the upper bound. So epsilon is first spent on setting this lower and upper bound, and then we are calculating uh, the actual sum. So if we could see the difference over here, let's say on the seventh day the number is 16039, but in this case, and with differential privacy in the earlier method, it's like 16688. So there is a lot of noise that's being added because we didn't have enough epsilon to do the spending for. So I mean, ideal case would be like if you don't know what's your lower and upper bound, you could use this method, but then a lot of epsilon would be spent actually on calculating this, or a lot of your privacy budget will be spent on calculating this part. Your calendar bounds. Now, let's move to the next step. So in the previous example, what we had assumed was like just a person just visits 4 times a week, actually not once a week. But sometimes, for example, in some example, we had assumed that a person just visits like 1 time a day. So that happens means like we are setting a lower bound of 10 and upper bound of 50. But what happens if a person visits multiple times a day? For example, he comes for lunch, dinner, so and even it's just breakfast. So breakfast might be costing him 10 euros, but the dinner is costing him 50 euros. So if we had set L in sensitivity in this case, what might have happened is what we do is we simply multiply this number. So, for example, in the internal mechanics, it's like we're multiplying L naught into L infinity sensitivity. We multiply these two, and a lot of noise would be added. So, when we had set this contributions to two, for example, a person might come in two times a day. What could happen is like the upper bound is multiplied by two, so it would be like 50 times two, so that would be like spending 100, but the actual amount that's being spent is actually 60. So that's the reason we are doing this pre-aggregation in this particular example. In a real world scenario, you might not need this aggregation. You could directly use L naught and L in, but in this particular example, we actually need to clamp this user, so limiting them to one per day. So let's just do that. So we are calling it getting private sum using pre-aggregation. So again, we are creating a bounded sum object, and then over here you could see that we are when you're creating the sum, we are also creating unique values of the sum. So for each user, they can only come in once since you're creating a dictionary and summing that up. So for example, a person spends 10 and 50, we are actually combining them to 60 rather than, so we are uh, creating a sum of them and just spitting out the result. So what we're gonna do is like we're gonna take this using differential private and using the normal manner, and we're gonna see what happens. So over here, as you could see that the numbers, actual number and with DP. So with DP and without DP, the numbers are actually very near as compared to the step earlier, where there was a bit of more error. So you could compare this with the previous value, and you would find that the noise over here might be a bit less compared to over there. So values might be more near because over there, our basic assumption was a person might just come once in a day. So if a person comes multiple times a day, he would be considered a different user. So that's something that we don't want. So what DP algorithms usually do is like they expect that a user just comes in once a time, like a record just appears once. So if in that case you might want to use L not in sensitivity and L in sensitivity. So there's a very good paper that folks at Google actually use, which can be found over here, and you could just find a paper. And also, if you want to see the reference demo, you could just click on this link. Already have the notebook, so you could try it out. So this finishes part two of the tutorial or the demo set, and the third demo is about like what's new in PyDP or how can we use PyDPs in distributed systems. So I'm just going to go through this real quick. Over here, our assumption is, for example, you have, let's consider our first data set. So we have like 5 records, 5 huge data sets. So, and we're just combining them together and we're seeing that the sum. Now, why we thought about this is like, for example, in a lot of scenarios, what happens is like your data is in a distributed manner, or you might be receiving stream of data. So, for example, as soon as the data comes, you want to give some results, or might be your system might be in a different manner. Say you have a distributed system, so or you have 5 clients who want some who want some results themselves, and they might send you the result, and then when you combine those results, you want to see those results. So in those cases, we are considering this in this scenario. So PyDP supports this differential distributed system. So okay, so what you're going to do is again we are creating a partial TP object over here. What we're gonna do is we're gonna split our data sets into two parts, one with 3,000 records and one with 2,000 records. And also one very cool thing about PyDP is like you could actually use partial privacy budget. So let's assume that you have like a privacy of like 100%. You could spend like 30% of privacy budget on some part, 30% of privacy budget on the other part, and then when you combine, you could just use the remaining part. So at the beginning, as you could see, we have 100% privacy. Now what you're gonna do is telling that when you're calculating the result, I'm telling that use 30% of privacy. We are calculating this result one. And now what I'm gonna do is this is actually sum, and there's a difference because we use partial DP, partial budget, privacy budget. And now what we're left with 70% of our budget. So we are gonna do again. We are gonna in this case we are gonna use all of our this thing. So what happens is like over here we had used 30% of result, and now what we are doing is we are actually adding entries to the same thing. So what happens like there was some data result calculated for the first 3,000 records. Now you could add it, and now like using the algorithm, it automatically calculates how much noise needs to be added, adjusts it accordingly, and like now remaining of this could be used. And when we are done with this calculation, so I'm left with zero budget. So I'm because I ran it again. So what I'm gonna do is I'm gonna reset the whole thing. So over here, just before starting this thing, say reset, running the same process again. And as you could see in this case, now we are left. We have used all our privacy budget, and now we have zero left. So now let's see like what was the actual difference. So what happens if we use private um, if we had spent 100% of this thing on the whole data set, and you could see that if we had just used 70% on the whole data set and what we had used like on the split data set. So what happens is like whenever you use the split condition, of course you need more budget and you might be adding more noise because of this partial process. And one thing I would encourage you to do is like go to the documentation. We have something known as serialize and merge functions. So that allows you to send data across various nodes. So the coming months, what you're gonna do is we're gonna integrate this with PyShift as well as PyGrid. So with that, you should be able to access remote tensors and do the EDA on those, and post that you could do the TP operations over there. So because of that functionality, we are putting the serialize. So serialize like okay, just think of it as like you're zipping the data and sending it over, and a merge is like when we want to merge this data to our own to our original bounded sum object. So that's it from for the demo side. Uh, so in the coming months, what we're gonna do is I think we're in short of time. So what we are do is like PyDP has become one stop for differential privacy rather than just Google's differential privacy package. So we're gonna add tons of noise mechanisms. Right now we just support Laplacian, but we're gonna add Gaussian, exponential, white noise, and tons of stuff. Other stuff what we're gonna do is we're gonna add database support. So right now you have to use list, but we're gonna right now we are in the but what we are doing is we are in the process of adding Postgres support right now. We're also gonna add MongoDB or other. We're gonna also add machine learning and deep learning capability within PyDP itself. So we are thinking in the process of adding this linear regression, PCA, logistic regression, and another fourth part is like the ETL process. So that's why like we expect most of the enterprises to use deep in the scenario. So for example, you want to generate some results on a huge data set, like for example, like for your 10 years data, you have a data warehouse and you want to generate some results. So this is where you could be using it. So Apache PIM is something that we are thinking of supporting in this coming future, but we could be open if there are any other ideas that needs to be done. So that's it. Thank you. You could contact me on Slack. It's at Red Chinmay, and on Twitter at Chinmay899. If you want to get involved with the PyDP team, you could contact us at lib_PyDP on Slack. And if you want to see the documentation, it's at pydp.readerdocs.org. So that's it from my side. Questions?
Okay, thanks a lot. Thanks a lot for today's session. It was really interesting to know more about PyDP and differential privacy concept. I can share the link to the project in the chat.
Okay, that's good. That's good.
Okay.
Thank you. Yeah.
Feel free to check the Q&A box if you would like to see if there is anyone who
Mm.
have questions. Otherwise, we can end the session.
Yeah, I think one question I think is already answered. So
Okay.
so I think we are good to go.
Okay.
Uh, yeah. Are there any other questions that needs to be answered? You could put it in Q&A box.
Okay. So, anyone has questions from this participant? So, I think it's okay. It's good to go. Then, thanks one more time, and we keep us updated about the library and of the upcoming change. And we'll see you soon. We hope.
Yeah. Yeah.
Thanks for.
Thank you everyone.
Thanks a lot.
Thank you.
Thanks. That
Thank you
was
everyone for joining us. Yeah. Thank
okay.
you, Shah, for holding us. Yeah. And I guess like if you want to get involved with PyDP, you could ping me on Slack as well as join PyDP team itself because we are adding more functionalities and we would like to have more team members. That's it. Yeah. Thank you, Jim.
That's it.
Thank you.
Thanks.